Bam! Mr. True! In this math lesson, we're going to be introduced to the concept of a vector. We're going to define it. We're going to look at the parts that make up a vector. We're going to define what equal vectors are, opposite vectors, the definition of a null vector, and then we're going to review the geometry and those geometric properties, some of them anyway, of a regular hexagon. And then using those geometric properties, we're going to define some vectors using the vertices of that regular hexagon that match or show that we're using and understanding these definitions introduced into this introductory video. And it is just an introduction to vectors. It's a geometric representation. We're not going to be doing a tremendous amount of math, just showing our understanding of the definition of vectors. And then through this vector chapter of mathematics, we're going to be building into an analytical representation of vectors and looking at all of that math and many applications and measurements that we can take in analyzing using vectors. As we build up that playlist, we'll have a link in the description of this video and every video that's related to this topic. Even some of the older ones I did many years ago when I had brown hair instead of gray. So at any rate, a vector. A vector is a quantity generally represented as a directed line segment. Now that's really important here, directed line segment. It's going to look like here, as you can already see, it looks like a ray, but it is not. So it's very careful of how you draw these diagrams. Having direction, which is going to be measured off of horizontal in a counterclockwise direction, just like you defined your angles for standard position angles. Though the initial point that you're seeing here does not have to be on the origin, as well as magnitude, in terms of its length, its magnitude, and then finally its direction. Now as you look at this vector that we have drawn, this vector AB, it has an initial point of A and a terminal point of B. Now, unlike a ray, which also has an initial point, this vector is not passing through B and extending on forever. It does not have a length of infinity. Vectors have a real length, a real magnitude, and that magnitude again represents things like wind speed and force and many other things in physics. Now all these parts make up this geometric representation of a vector, and when you write out your notation with AB and a little arrow above it, similar to a ray in simple geometry, our arrow is going to start where the initial point is going to be where that arrow starts, and the point of that arrow is going to be ending above the terminal point. Now as you draw your vectors, do not extend this arrow, this thing that looks like a ray, beyond B, because then you're misrepresenting the magnitude of that vector, and do not allow it to fall short either. This is not a ray going on forever. It is a directed line segment starting and ending at those two endpoints. Now AB usually represents either the position vector of B. You're not going to see this necessarily in this section, but in the upcoming ones, this sentence or this part of the sentence will make more sense. When you look at an analytical representation of a vector, it looks very similar, one of its formats anyway, it looks very similar to the coordinate of a point, but it's going to have a little bit of different notation. And that's where you have to remember that while a coordinate, say, of 2, 3 and vector 2, 3 look similar, when you want to plot a coordinate, you have to start at the origin of 0, 0 and then move left and right and up and down, just like with the vector. But with a vector, that initial point can be anywhere. That's why we say that this vector represents either the position of B, position vector of B relative to its initial point A, or the displacement from A to B. Now equal vectors have the same direction and magnitude. We're not going to do the mathematics of this. We're not going to even break out protractors and straight edges, just kind of eyeball it roughly. And opposite vectors have the same magnitude, but opposite direction. We'll be actually doing the mathematics of analyzing these values of magnitude and direction upcoming very, very soon. But they have the same magnitude, but the opposite direction. In other words, this angle, you're probably measuring it right now in degrees, but it could also be in radians. An opposite vector those opposite vectors are going to be separated by either 180 degrees. So say instead of a rotation of, say, 30 degrees, you're rotating 210, or pi over, what, 6 and 7 pi over 6. Those are called opposite vectors, or maybe negative vectors. So again, opposite vectors have the same magnitude but opposite direction, also called a vector's negative. So in blue, like our definition here of equal vectors, they have the same direction and magnitude. So equal vectors does not mean that you have to have the exact same initial point and the same terminal point and go in the same direction, but we can draw a vector with this sort of direction and this magnitude or length, but use the word magnitude, anywhere on the chalkboard, and as long as it's reasonably done, unless your teacher is requiring you to use a straight edge and protractor, as long as we have that same direction and same length, we can call it AB and just have another vector AB in space. We can even call it vector CD. So vector CD is equal to vector AB. Or we can label that vector with just a simple letter. We can say this is vector V. So vector CD, or maybe we want to call it vector V. You'd have to have some kind of single letter label somewhere in the middle of that vector between the initial and terminal point. But vector V is equal to vector CD, which is equal to vector AB. Now, with some orange chalk, if I draw a line segment with the same length and parallel, okay. So right now, we just have a line segment. Now if I come through here and I say that this is also A and B, maybe A sub 1 and B sub 1, but instead of having the arrow, or the, the arrow sort of appear to start from A and go to B, if I bring that in the other direction and say, well, okay, B is now going to be my initial point, and I'm going to identify that by having the arrow go towards A and stop at point A. Well, now this vector, assuming this is the same length and the same direction, is, well, the negative of AB, or its vector BA. So this white, or now blue vector, and this orange vector have the same length. They're in the same direction, if you will, except for I've said the word parallel, but we're just doing this geometrically. If you have to measure the direction of an angle off of the initial point, which you do, this angle here, theta 2, and this angle here of theta 1, this angle is 180 degrees more than this angle, or this angle is pi radians more than this angle. Now, if you think back in trig with your coterminal angles, this could be multiple rotations, but there was some multiple or relationship where I want to say a multiple of 360 or 2 pi, but any angle which is any angle that's coterminal to this one that ultimately has a relationship of being 180 degrees away or in the opposite direction of theta 1 is going to be considered an opposite angle. Now let's move on to a zero or null vector. The magnitude of vector AB is the length of AB, and denoted by sort of what look like absolute value brackets wrapped around that vector of AB. So again, if we want to denote the length of a segment, like in geometry, if you had just a bar here with no arrows, just a straight line segment above AB, that would indicate segment AB, no indication of whether it's a line or a ray or a segment above those letters, it was length. But when you're talking about vectors, we just take that vector notation, wrap it in a set of what look like absolute value symbols, and we say we're looking for the magnitude of vector AB, its length. Or a single letter denoting that vector, if that may be matching the notation you're using in your problem or given. And your magnitude is a non-negative scalar, just simply a number that you're multiplying to this vector, and it indicates a length, and length cannot be negative. That negative vector, right, in the opposite vector is just indicated in opposite direction. So it's an indication of direction, not length. So length cannot be negative, magnitude therefore cannot be negative. A zero vector, otherwise called a trivial vector or a null vector, depending on the textbook you're learning from and your teacher, well, that has a magnitude of 0. Whenever you see a vector denoted by the same point, both initial and terminal, well, then you have a vector that has no defined direction and a magnitude of 0. It's a trivial vector. Now we're going to have this given where we have this vector, not vector, but hexagon, regular hexagon, A, B, C, D, E, F. Now, being told that this is a regular hexagon, we have to understand what that means. That means that all of the sides around the outside of this polynomial are equal, and the measure of each of these interior angles is also equal. I'm going to take the time to break down the geometry of this regular hexagon to answer this and 2 more questions, because, well, last year was the first time I taught IB mathematics, and at my school, and maybe yours as well, they have to go very, very quickly through geometry. So I found out that even my most advanced math students were at times a little bit weaker in geometry than I expected. So how are we going to show that vector FA is equal to vector DC, that these vectors have, and I can highlight this maybe, vector FA and vector DC, what's going to make those 2 vectors equal? How are we going to show that those 2 vectors have the same length and same direction? I'm afraid maybe the green's not going to highlight too well against the yellow. I'm not sure about the blue either, but hopefully the camera's picking this up. Well, to answer that question or show it, explain why, we need to know the geometry that's going on with this regular hexagon. Well, again, it's regular. So that means that each of these, let's see here, each of these sides are going to be equal. That's going to take care of the first requirement, that the magnitudes are equal. And this is beyond maybe the scope of the class a little bit, but if we extend, and not necessarily, it depends on how you look at it, may or may not be considered necessary for this question, but if you extend out these sides in some direction, whether it's all clockwise or counterclockwise, you have a bunch of external angles. Now, those external angles for any polygon have to add up to 360. And since each of these angles are equal, each exterior angle is 60 degrees. Now, the interior angles, there's 2 ways of finding the sum of the interior angles. Each exterior angle and interior angle form a linear pair. They're 2 adjacent angles that form a straight line. And linear pairs are supplementary. So each of these interior angles are equal to 180 minus 60. Now that's one way of finding the measure of one of these interior angles. Or another is the sum of the interior angles. While the exterior angles always have a sum of 360, the sum of the interior angles is equal to the number of sides of any polygon. Actually, it doesn't have to be regular. In this case, it's 6. The number of sides minus 2 times 180. That 6 minus 2 is coming from the fact that in this polygon, any polygon actually, if you pick a vertice and draw diagonals from that vertice to all the other diagonals that doesn't share, where you don't share already a side, you're going to have 1, 2, 3, 4, or 2 fewer triangles from the number of sides a polygon has, and the interior sum of a triangle is 180 degrees. So 4 times 180, or 120 times 6 is equal to 720 degrees. Now, why am I bringing all this up? Well, we have to show that not only the magnitude of these 2 vertexes are equal, but they're in the same direction. that this angle is the same as this angle. Basically, that those two lines, the line defined by the points of AB and the line defined with the points of DC, are parallel. Now, we can see that this vector is going up to the right and this vector is going up to the right. So as long as we show that those two lines defined by FA and DC are parallel, I'm going to be happy with the fact that we've shown that these vectors go in the same direction, not just have the same magnitude. Well, I've got these dotted line segments going through this regular hexagon, and actually maybe want to go probably beyond the scope of your book, or maybe the requirements they're asking you to do to show this, but I want to look at this line segment as a transversal. But if I don't truly understand what's happening with all the angles inside this polygon, I drew these as going to the center of this hexagon. Now, if this were a pentagon, then from vertex to center to another vertex would not form a straight line. I want to make sure that we validate and we understand that this red line segment going from A through O to the other vertice of D is actually a line and not two broken or just simply two line segments. So let's take a look at the fact that we have a central angle here that's equal to, any full rotation is equal to 360 degrees, and this is broken up by 1, 2, 3, 4, 5, 6 angles, and this is a regular polygon, so each of those angles are going to be equal. So this angle here of EOD is going to be equal to 360 divided by 6. So we're looking at EOD, and this is 60 degrees. Okay, whoop-de-doo. Well, inside this triangle, we have segment EO and OD, both of which are basically radiuses, if you will, for this hexagon. This regular hexagon could be inscribed in a circle, each of these vertices being on that circle. That's true for any regular polygon. So these are radiuses, and therefore they're going to be, if this were inscribed in a circle, are going to be equal. Now, inside of this triangle, we have a total sum of 180. Well, the interior sum is equal to that, what I said, 180. Take away this angle of 60 degrees, leaving us with 120 degrees, the same measure as each of those interior angles, by the way. And if you have a triangle whose two legs are congruent, then the angles opposite those congruent sides, I think I said angles, but those two congruent sides, the angles opposite those two congruent sides, the base angles, have to be equal, like the sides for which they're opposite to. So that 120 divided by 2 is equal to 60 degrees. Okay, so what do we have going on here? We have 60, 60, 60. Well, that adds up to 180 degrees. These three adjacent angles have a sum of 180 degrees, adjacent angles. Therefore, this is actually a line segment, or a line, not two segments. And this angle here is 60 degrees because, well, we just showed that with our geometry. By the way, if that's 60, if all of these angles are 60, then this is actually not just an isosceles triangle, but an equilateral triangle. And when you have two lines being cut by a transversal, and here's one triangle with an angle of 60, here's one triangle with all these angles actually being 60. When two lines are being cut by a transversal and the alternate interior angles are equal, then those lines are themselves parallel. So I'm going to step off and pause the camera and write this out, but basically the fact that this is a regular polygon justified that the magnitude of FA is equal to the magnitude of DC, and with a little bit of understanding of geometry, and maybe a few more facts that maybe you didn't necessarily need to use for this, but we have validated with our properties of two lines being cut by a transversal, showing that these line segments are parallel. Thus, the direction of vector FA is equal to the direction of vector DC, and since their magnitude and direction are equal, those vectors themselves are equal. No, 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 no. Bam! We got that done. Now we're going to be using the vertices. Name all the vertices which have the same direction as vector BC. So the rest of these questions are going to be focused on, let's do this in orange so it stands out. We're going to be looking at vector B using the vertices. Name all the vectors which have the same direction. Now a lot of students will say, okay, we have to look at this hexagon, use the same vertices, and they just focus on the sides of the vertice and give an answer of, well, BC going down to the right. So how about another parallel line segment down to the right, FE. Now I keep saying parallel, but these are directed line segments, so quote-unquote parallel could end up getting you in trouble and saying, well, let's just do this. EF. Is that in the same direction? It's, if I focus on just a segment of parallel lines, then it's parallel, but EF is going up to the left, whereas BC is going down to the right. These are actually, if I give this as an answer, I haven't given a vector who has the same direction, but an opposite direction. This is the sort of negative vector or opposite vector to BC. That's not the same direction. We want to put down an answer of FE. Now don't get fooled into thinking that that's the only answer. It says using the vertices, not using the sides of the regular hexagon. So there's another vertice here. Now O is not a vertice, but there is a vertex defined by the vertices of A and D, which is going in the same direction as BC. So vector AD is your second answer. And the two answers to this particular question. Now, I want the same magnitude as BC. Magnitude, length. And that's it. Well, it's a regular hexagon. And only using the vertices, not the center, well, that would be vector AB. And a student could write vector BA and write out all of those opposite pair. I'm going to go ahead and just, well, let's go ahead and do that. Some of your textbooks may just give like one set. They'll just consider these opposite vectors as sort of the same answer. So we have vector AB and BA. We have vector FA and AF. We have vector FE and EF, ED. Whoa, stepping on my other chalkboard, which I do truly prefer more than whiteboards. DC, because you throw almost nothing in the garbage and not add to all the plastics in the world. And CD. Okay, so basically we have 1, 2, 3, 4, the other 5 sides, and you can give 5 answers, or maybe your teacher's looking for you to write out those opposite vectors as well, because they do technically have the same magnitude and are a different vector. Now, is it possible to define a pair of non-trivial equivalent vectors? Okay, so non-trivial. So we have to name vectors that do not have a magnitude of 0 and actually have a directed or a direction, a directed line segment, right? And equivalent vectors. We've actually already done that. So of course the answer is yes. The answer is not always going to be yes for all polygons, but for this hexagon, that's exactly what we did in part A. We had 2 vectors and we showed through properties and reviewing of geometry, properties of hexagons, that those actually were equal vectors. So yes, of course, we already did it. And you can say it's vector FA and DC, of course. And I'm going to ignore the opposite direction now. How about FE and BC, where they're both going down to the right. And F, we don't have an AB yet. So vector AB and vector E. And that is the end of our first introduction to a geometric representation of vectors. I hope you learned something. I'm Mr. Drew. Bam! Go do your homework.